In this video, we're going to go over the 2018 summer final exam for MAT401. The course in 2018 was instructed by Jonathan Korman and was also instructed by the same professor this year, 2024 winter, when I took it as well. We had an autofail policy, and presumably they had one back then as well. And what that simply meant was that you needed to pass the final exam to actually pass the entire course. Now, while that definitely may sound scary, the exam obviously can't be so hard that too many students fail, so as long as you were keeping up with the material throughout the semester, you were honestly fine for the final exam. So let's jump into the first question. So for question 1, we're dealing with this ring over here, which is the ring of polynomials with coefficients in Z mod 5, and we're looking at this ideal over here. So let's take a look at part A. We want to show that I here is a maximal ideal. So let's go into that. So first, we can observe that since Z mod 5 here is a field, we know that this ring over here is a principal ideal domain. So principal ideal domain. So what that simply means is that every single ideal of this ring is generated by a single element. That's what it means for an ideal to be a principal ideal. And from this, we can conclude that this ideal over here is maximal if and only if the polynomial that generates it is irreducible itself. So from this, say thus, this ideal here generated by x squared plus x plus 2, it's maximal if and only if, let's just call it p of x, is irreducible. Now, since the polynomial we're dealing with is a quadratic, meaning degree 2, we know that's irreducible if and only if it has no roots in the field we're looking at, which in this case is Z mod 5. So let's quickly write that out. So we know that, again, p of x is irreducible over Z mod 5, if and only if it has no roots in Z5, and we can quickly write out explicitly what those elements look like. It's just 0, 1, 2, 3, and 4. And again, usually you might see it with like bar notation, but in this case it's kind of implicitly understood that we're just dealing with the integers mod 5. So now again, because we have a quadratic, it's degree 2, and this again works for degree 3 as well, we can simply plug in all of the elements of this field because it's finite and it's very much reasonable to check because there are only 5 elements. So let's quickly do that. So here we have p of 0. We can evaluate that. So we get 0 plus 0 plus 2. This is just equal to 2, which is clearly not equal to 0. We do the same for p of 1. So we get 1 squared, which is 1, plus 1 plus 2, which gives you 4, which is again not 0. Check p of 2. So 2 squared is 4, plus 2 plus 2. So here we get 8 mod 5. This is just equal to 3, which is again not equal to 0. We can check 3. So 3 squared is 9. Plus 2, plus 3 plus 2. So we get 12 plus 2, so 14, and then 14 mod 5, we can just subtract 10 to get 4 again, which is again just not equal to 0. And finally, we can check p of 4. 4 squared is 16, plus 4, so 20, plus 2 would be 22, but then 22 we can mod out by 5 again, so we're effectively subtracting 20 at 2, which is again not equal to 0. We can note that none of these values over here are 0, right? So none are 0, and that simply means that none of these values are actually roots of this polynomial, and hence we can conclude that p of x has no roots in Z5. Which is also enough to claim that, or support our claim that p of x is irreducible over Z mod 5. And that completes part A. So let's take a look at part B now. So part B asks us to find the GCD of 2x plus 3 and that same polynomial we were looking at, x squared plus x plus 2 in Z mod 5, or in this ring of polynomials. So because the polynomial we're dealing with here, we just show that it's irreducible. We know that its only divisors are 1 in itself, but I'm just going to use the division algorithm, which will kind of speed up part C, because you'll eventually have to use it anyways. So let's do that. Again, we divide the higher degree polynomial by the lower degree polynomial. So we could set it up as follows. So here we have part B. So we have 2x plus 3. Then we have our x squared plus x plus 2. So again, here it's key to remember that we're working over Z mod 5. So the way we carry out the division algorithm changes very slightly, but the concepts are still the same. So here we effectively want to multiply this by something so that we can get rid of this x squared term. So in this case, you're thinking to yourself, what can you multiply? Again, we're focusing on this 2x. What can we multiply 2x by, or mainly just 2 here, to get a 1, right? Again, we're working in Z mod 5, so if you want a 1, you can also get a 6 by just adding 5. So here we can multiply by 3x. And if we multiply that out, so again, 3x times 2x will give you 6x, but again, because we're working in Z mod 5, that just becomes x. And then 3x times 3 is 9x, mod 5 is just 4x. So plus 4x. And then now we can just subtract. So, oops, this should be x squared. So x squared minus x squared is 0, and then you have, and we don't have to write that, and then we have x minus 4x, which is negative 3x, but of course, again, mod 5, we can add a 5 to that to get 2x, and then plus 2. And then we can repeat that same process, but it's a bit easier. In this case, we can just multiply by a 1, so plus 1, and then we can subtract off 2x plus 3. So again, 2x minus 2x will give you 0, and 2 minus 3 will give you negative 1. In this case, I'm going to leave it as negative 1. We could easily rewrite it in terms of mod 5, so within these elements over here. But for our later purposes, you'll see that it's going to be easier if we just leave it like this. So again, with GCD, remember, we're only looking for a monic. So it doesn't even matter if it's just some constant. As long as it's a linear term, we know we're on the right track. So again, we can now just conclude that. So therefore, the GCD of 2x plus 3 and x squared plus x plus 2 as a monic is simply just 1. Cool. Let's move on to part C now. So in part C, we're asked to find the multiplicative inverse of 2x plus 3 plus I in this quotient ring over here. So again, we can still treat this as just 2x plus 3 as a polynomial. We're simply just working in this quotient ring instead. And yeah, so again, let's remind ourselves of what we're looking for when we're looking for a multiplicative inverse. We're simply looking for a polynomial where when we multiply this, we get the identity, which in this case is just 1. A really nice way to do that is we can simply use the extended Euclidean algorithm. So this division algorithm we were using over here, we can also just call it the Euclidean algorithm, but we can use the extended Euclidean algorithm to rewrite the GCD, or to express the GCD as a linear combination of the two values that we're actually looking at. So let's do that. So first we can take a look at what we have here. So we know that the general kind of formula or equation we go by is that the dividend, so this value here, is equivalent to the divisor times the quotient plus the remainder, right? So we can first rewrite that. So we have our dividend, so x squared plus x plus 2. This is equal to 2x plus 3 times 3x plus 1, and then plus negative 1, so just minus 1. And of course, we can now rearrange this so that we get the sum of some terms is equal to 1. Right? So we can add over this 1 and then subtract this over. So this is what we have. So we have that 1 is equal to 2x plus 3 times 3x plus 1, and then minus x squared plus x plus 2. Oops, x plus 2. Perfect. And then in this next step over here, we're going to make use of the fact that we're actually working in Z mod 5, like this ring of polynomials modded out by I. And when we mod out by this ideal over here, we can effectively treat this polynomial here as 0 now. Right? So In that case, then we know that this entire thing just goes to 0. So we know that we then have 1 is equal to 2x plus 3 times 3x plus 1. But hey, notice, this is actually exactly what we want, right? We have our 2x plus 3. We're looking for the multiplicative inverse, meaning we're looking for what can we multiply this value here by to get 1. Well, here it is. It's exactly 3x plus 1. And of course, you can verify that if you multiply this out, you will get something of the form x squared plus x plus 2. And somehow things will cancel out. You'll be left with a 1. Definitely verify this as an exercise, but you can also take my word for it. So we can write up the conclusion really quickly. So therefore, the multiplicative inverse of 2x plus 3 is, and it's precisely just 3x plus 1. And that's question 1. Question 2, let's look at part A. So we want to find the splitting field E for this polynomial. Again, now we're working over Z mod 3. As a quick reminder, the definition of splitting field, we're simply looking for the smallest field such that this polynomial here, it can factor into linear terms. So first, let's see if we can factor x to the 4 minus x squared minus 2 a little bit, see what we can do with it. So for A, so we have x to the 4 minus x squared minus 2. Of course, you can also rewrite the coefficients in terms of elements of Z3, which is again just 0, 1, and 2. But for now, we can leave it like this so we can express it a little differently. So notice that we can actually factor this as follows. So we get x squared minus 2 times x squared minus 2, which of course we can just rewrite this as x squared minus 2 squared. Now to find a root, we can set this expression equal to 0. So for a root, we can set this to 0, so set, actually let's write it this way, so we can set to 0. So we have x squared minus 2 squared is equal to 0. And actually I'll continue over here, so continuing from here, we can obviously take the square root of both sides in this case, so we have x squared minus 2 is equal to 0. And of course adding 2 to both sides, we have x squared is equal to 2, which in Z mod 3 is equal to -1. So I'm realizing you can actually leave it as 2 or -1. It'll work either way. So now we can just let alpha be a root of this polynomial. Right, so let alpha be a root of x to the 4 minus x squared minus 2. And this is actually in a field, so in a field extension. So in a field extension E. From the brief bit of factoring work we just did, we can see that any root alpha, so alpha must satisfy. So this equation over here, or these set of equations, but more easily we can kind of phrase it over here. So we just have alpha squared is equal to -1. And from this, so we can then conclude that and thus the splitting field of this polynomial, so must be Z3 adjoined alpha. So we can quickly take a look at our factoring that we did over here. The only thing that's kind of giving us a problem in some sense is just this x squared minus 2 term, right? Because this is what we're not able to factor further. If this was some other quadratic, cubic, whatever term that was producing more roots that we didn't have in Z3, we definitely have to adjoin more elements. But in our case, because we just have the same x squared minus 2, adjoining some root alpha over here that satisfies alpha squared is equal to -1, whatever that alpha may be, as long as it does satisfy this, we know that we are then able to further factor this right over here, which then gives us the splitting field precisely. Now let's take a look at part B. We want to find how many elements E has. So again, we have E, we said it was equivalent to just Z3 adjoin alpha. And we can express this as a set, but just really quickly, what we're really doing by adjoining alpha is that we're just adjoining all powers of alpha. But because we know that alpha squared is -1, which again is an element of Z3. If you just add 3 to it, it's basically 2. We know that all higher powers of alpha can effectively be expressed as just a singular alpha unit as well as other elements in Z3. So we actually don't need all the powers of alpha in our definition. It's kind of implicitly included in some sense. So let's quickly write that out. So we effectively have elements of the form a plus b alpha, where a and b are in Z3. And the really big shortcut here is that we know that a and b are in Z3, which has 3 elements. So we have 3 choices for each a and b. So effectively, we have 9 total elements, but we'll quickly see explicitly what those 9 elements are. So to see them, we can simply just take different values of a and b within Z3. So first, we can just simply fix b to be 0, and then we just have Z3 elements. So we have 0, 1, and 2. And now we can fix a to be 0. So if a is 0, and let's say b is 0, then obviously we still have 0. A is 0, b is 1, we have alpha, then we have 2 alpha. And then now we can just simply mix and match, right? So if a is, let's say, 1, b is 1, 1 plus alpha, 1 plus 2 alpha, and then I think you also have 2 plus 2 alpha. Let's see how many we have here. So 1, 2, 3, 4, 5, 6, 7, 8. We're still missing 1. We're missing 2 plus alpha, I believe. Yeah, 2 plus alpha as well. So this is where a is 2 and b is 1. So these are the precise 9 elements. And then we can just write a quick conclusion. So we can say, therefore, E here, our splitting field, has 9 elements. Question 3. Let K here be an algebraic extension of Q adjoined root 2. We want to show that K is an algebraic extension of Q. So first of all, an element is algebraic over a field simply if it is the root of some polynomial. And then we can kind of extend that to an algebraic extension where every single element of that extension is algebraic. So in our case, we can draw a quick little diagram over here on the right, or on the left, sorry. So we have K here, and we're going to have Q adjoined root 2. Then we're going to have Q. So again, if we have an algebraic extension, it means that all elements of K are going to be the root of some polynomial in Q adjoined root 2. All right, let's begin. So first, we're going to just let K be an algebraic extension of Q adjoined root 2. So again, as I mentioned, this means that every element in K is algebraic over Q adjoined root 2. Right, so every element in K is the root of some polynomial with coefficients in Q adjoined root 2. So let's proceed with a hint and take an element alpha in K. So we can say let alpha be in K, meaning alpha is algebraic over Q adjoined root 2. And so there does indeed exist, so there exists a polynomial as coefficients, in Q adjoined root 2 with alpha as a root, so with alpha as a root. So let's call this polynomial f of x. Let's do it here. So let's say it's f of x. And we can write it as a generic polynomial, so a0 plus a1x all the way to an x to the n. And again, because alpha is indeed a root of this polynomial, we have that f of alpha must equal to 0. It's also important to note here that all of these coefficients here are in Q adjoined root 2. So let's quickly write that here. So a0 all the way to an are in Q adjoined root 2. So from here, we can do some manipulations to try to work in Q instead of just Q adjoined root 2. So then, and we'll start with f of alpha. We'll just work by plugging in alpha into this equation over here. So we have f of alpha. This is equal to a0 plus a1x all the way up to an x to the n. And of course, all of these coefficients here, I'll quickly note. So, or actually we noted over here. Again, they're in Q adjoint root 2. But all elements of Q adjoint root 2, similar to the previous problem with Z3 adjoint alpha, we can express in a very similar way because again, root 2, it's quadratic in some sense, it's degree 2, because after you square it, you get back into the rationals. And I think I wrote it up here. We can express all elements in this form, so we can effectively replace all of the AIs with something of this form. Of course, we'll use, I think we'll use beta and gamma in this case, and we'll use different subscripts. So let's do that. So we have, again, all of these are in Q adjoint root 2, so we can replace them accordingly. So beta naught plus, or beta 1, beta gamma, and then root 2 plus beta 1, gamma 1, root 2, alpha. This is going all the way up to beta n plus gamma n, root 2, alpha to the power n. And again, it's really important to note here that all the beta I and gamma I are in Q now. So not just Q adjoint root 2, but Q. So we're working kind of in a lower field now. From here, we can expand briefly. So we can drop some of the brackets. So B0 or beta 0 plus gamma 0 root 2. And then now we're going to multiply the alphas in. It seems a little counterintuitive, but we need to do some regrouping to eventually multiply something so we can kind of get rid of these root 2's to truly be working in Q. So let's do that. So plus beta 1 alpha plus gamma 1 root 2 alpha all the way up to beta n alpha plus gamma n root 2 alpha to the n. And then finally we can group these together sort of by betas and gammas now. So we have beta 0 or beta naught plus beta 1 alpha all the way up to beta n alpha to the n. And now if we focus on the gammas, we can do something very similar. So we have gamma naught, but in this case we're going to focus not on the root 2's, we're going to have that on the outside. We're kind of going to think about it as like factoring it out in some sense. So we have gamma 0 plus gamma 1 alpha. This is going all the way up to gamma n alpha to the power of n. But of course, we're multiplying the root 2 on the outside. So just to summarize what we did in this step, we're simply just rearranging all of these terms so that we're kind of grouping the beta alphas and the gamma alphas together. And the root 2, we're kind of thinking of pulling it out so that we can actually work with it a bit more. So if we think back to just high school math, if we ever want to kind of get rid of a square rooted number, the first thing that should come to mind is multiplying by the conjugate somehow, some way, right? But in this case, it's a little more abstract, not too much, but we can definitely multiply by the conjugates of these elements. We can kind of think of these as like just big A and B, so you have something of the form like A plus B root 2. So of course, the conjugate of this would simply just be to be multiplying by A minus B root 2. But in this case, let's just call this big beta instead, and this, or big beta, or capital beta, this as capital gamma. And I'll write over here, so we're just multiplying by the conjugates. So let's say here multiply by the conjugate. And now we can continue. So again, effectively we have big beta plus gamma root 2 times big beta minus gamma root 2. And again, this is all equal to 0, right? Because we have that alpha is algebraic. It's the root of some polynomial. This is just some generic polynomial, and we just have that f of alpha is equal to 0. So we know that this is equal to 0. And from here, we can actually multiply this out very easily. We can just use the difference of squares formula. You can think of this as like a plus b, a minus b. So we just have a squared minus b squared. So we have b squared minus 2 gamma squared. This is equal to 0. But this right here is precisely a polynomial with rational coefficients. So I'll quickly write that out. So we can say, therefore, big beta squared minus gamma squared root 2. This thing is a polynomial, or sorry, this is 2 gamma squared. It is a polynomial with rational coefficients, so coefficients in Q, and it also has, and with alpha as a root, and thus this just allows us to conclude that K is indeed an algebraic extension. So K is an algebraic extension, right? We know this is true again because we started out with some arbitrary choice for alpha. We didn't pick any choice of alpha, it'll work. And that concludes question 3. So here's question 4. We recall that the finite field with p to the n elements, this is the Galois field, again, of p to the n elements, it is the splitting field of this generic polynomial x to the power of p to the n minus x over the field zp. And we're reminded that if m divides n, then we have that p to the m minus 1 divides p to the n minus 1, and we have this useful kind of result over here as well. So let's take a look at part A. Right, so in part A, we want to show that if m divides n, then we have that x to the p to the m minus 1 divides x to the p to the n minus 1 in the ring of polynomials with coefficients in ZP. So first, let's assume the if part. Right, so suppose m divides n, and we want to show that x to the p to the m minus 1 divides x to the p to the n minus 1. So first I'm going to expand some things over here so that we can get a better sense of what we're actually trying to show. So this right over here, just using the definition of what it means for something to divide something, we can express this as x to the p to the n minus 1 it's equal to our x to the p to the m minus 1 times something. Let's just call it L for now. It's very generic just to show what it's going to look like. In addition, we can use the hint or the useful note over here that if m divides n, which again we are supposing is true, we then have this result over here. So p to the m minus 1 divides p to the n minus 1. And of course, we can expand it in a very similar fashion. So p to the n minus 1 is just a multiple of p to the m minus 1. So let's say multiplied by k. So from here now, because we're eventually trying to show that this equality here is true, we can start with this and make use of this right over here and proceed from there. So let's do that. So we'll start with the left side, so x to the p to the n minus 1, and this is actually just equal, so we have this equality over here, so we can replace p to the n minus 1 with p to the m minus 1 in brackets times k. So this is x to the p to the m minus 1 times k minus 1, but of course we can just re-express this exponent as follows. So x to the p to the m minus 1 all to the power of k minus 1. And as a quick reminder, in general, when we have something of the form y to the k minus 1, or sorry, just y to the k minus 1 like this, we can always express it or factor it as y minus 1 times y to the k minus 1 plus all the way up to just 1. So we're going to make use of this, and we can continue as follows. So we can kind of see the resemblance to what we have going on over here and over here. So you can always treat this as y. So you know that you're going to have something in the form y minus 1 times y to the k minus 1 all the way to 1. So we can just replace y with this entire term right over here. So this gives us x to the power of m minus 1 minus 1 times x to the p, so x to the p to the m minus 1 to the power of k minus 1 plus all the way up to just 1. But note that this is precisely in the form that we actually needed it, right? So this is the statement we wanted to show. This is completely equivalent to that. So here we have the x to the p to the m minus 1 minus 1 right over here, or sorry, right over here. And you can treat this as your L term, effectively. So we can write the conclusion here. So therefore, this x to the p to the m minus 1. I realize I added some brackets here, but that doesn't make that big of a difference. This minus 1 does indeed divide x to the p to the n minus 1 minus 1. It says as needed. So that's part A. Now let's take a look at part B. So in part B, here we want to show that, we want to use part A to show that any 0 of x to the p to the m minus x is a 0 of x to the p to the n minus x. So of course this is equivalent to saying that if some element is a 0 of this term, it's also a 0 of this term. It's like an if-then statement. So first we can suppose that we have some root or some 0 of this term over here. So let's suppose that, suppose that alpha is a root of x to the p to the m minus x. And of course, what we eventually want to show that is that alpha is also a root of x to the p to the n minus x as well. So we can actually start there and then try to manipulate a bit. So then we have x to the p, or well, we'll plug in alpha in this case. So alpha to the p to the m minus alpha. We can of course factor out an alpha. So we have alpha to the p to the m, or just alpha, sorry. Alpha times alpha to the p, sorry, there should be p to the n. So sorry, again, we're starting with p to the n, x to the p to the n minus x, and we eventually want to show that alpha is a root of this. So alpha to the p to the n minus 1 minus 1. This again comes from just factoring out alpha. And then from there, we can make use of a result from part A, right? We know that x to the p to the n minus 1 minus 1 is equivalent to precisely this right over here. So we can replace that. So we have alpha. So again, this getting replaced. So we have alpha, I'm going to drop the brackets, p to the m minus 1 minus 1 times x to the p to the m minus 1 to the k minus 1 all the way up to 1. And here we can multiply the alpha back in. So we have alpha to the p to the m minus alpha times, again, all of this junk over here. So we have x to the p to the m minus 1, again to the k minus 1, all the way down to 1. But notice that in our assumption again, alpha is a root of precisely this, right? And what this then tells us here is that alpha to the p to the m minus alpha is equal to 0. That is precisely what we have over here. So what this term here effectively is just 0 times whatever this junk is, which is ultimately, and here, just 0. And so from here we can just conclude that indeed, so therefore alpha is a root of x to the p to the n minus x as needed. Okay, on to part C. So in part C, we want to make use of part B to conclude that the Galois field with p to the m elements is a subset of the Galois field with p to the n elements. So first, let me make a quick note over here. So in part C, so first we can note that the Galois field with p to the m elements, so this term here is the splitting field of this polynomial here, so x to the p to the m minus x, and we can write it something similar for the Galois field of p to the n elements. So, and Galois field of p to the n elements is the splitting field of x to the p to the n minus x. And now, more broadly speaking, we know that the splitting field of each of these polynomials are simply just zp adjoined all of the roots. So I'll quickly write that out. So the Galois fields of p to the n is the same as, so again, zp adjoined all the roots of x to the p to the, actually I think, yeah, well, we'll go in the same order, so m here, so p to the m, p to the m minus x, and again, similar statement, so gf p to the n is the same as zp adjoined all the roots of x to the p to the n minus x. But remember, from part B, we have that all of the roots of precisely this polynomial over here are also roots of this polynomial that we have down over here. All right, so let's quickly write that out. So by part B, all roots x to the p to the m minus x are also roots of x to the p to the n minus x. So again, what that really just means is that the roots of x to the p to the m minus x, that if you think of that as a set, it's a subset of the roots of x to the p to the n minus x as well. So also the roots of this, and then we can then conclude so and so. The roots of x to the p to the m minus x, again, just as I mentioned, are subsets of the roots of x to the p to the n minus x. And together with this, we can conclude exactly what we wanted to show in part C, which is that the Galois fields are indeed subsets of each other. So I'm just quickly write that here. Oops. So hence, the Galois field of p to the m elements is indeed a subset of the Galois field of p to the n elements as needed. Question 5. So we have f of x in this ring of polynomials with coefficients in f. It's an irreducible polynomial over f. We're letting e be its splitting field over f. So we want to prove that all zeros of f of x in e have the same multiplicity. Okay, so first we'll set up the question, and then we'll go into the more useful definition of multiplicity in this question. So first, let alpha, beta in E be roots of f of x. So here's the definition of multiplicity that we're going to go with. So I have it here. So multiplicity is the largest integer. We're just going to call it m sub alpha in this case here, such that f of alpha is equal to 0, and then we're looking at the higher order derivatives here as well. So f, the, I guess, first derivative of alpha, or of f evaluated at alpha is equal to 0. Second, all the way up to the m sub alpha minus 1th derivative. This is equal to 0. And then obviously the m alpha derivative is just not going to equal to 0. So we want to show that all zeros have the same multiplicity, but of course it's a little difficult to show that directly, so we can proceed by contradiction. So here we can suppose for a contradiction that the multiplicities are not the same. So in this case, our multiplicities, we're just going to call them m sub alpha and m sub beta. So again, without loss of generality, m alpha is greater than m beta. So again, what this basically means is that even if we were to kind of reverse this or swap them, the proof would effectively proceed in the same way. So what we have here, this means that this term over here, so f to the m alpha minus 1, this is equal to 0, but m sub alpha minus 1 evaluated at beta, this is not equal to 0, right? So again, this directly follows from our definition of multiplicity, and we're going to work towards finding some kind of contradiction here so that we can actually conclude that this assumption here that they're different was indeed false, so they must be the same. So we'll proceed by using the hint that if alpha and beta are two roots of some polynomial f of x, then there is an isomorphism going from f adjoint alpha to f adjoint beta that fixes f pointwise and takes alpha to beta. So what that means is that it fixes all elements in f, meaning if it's an element in f, sigma of that element is just going to be itself. So it kind of acts like the identity on f. And it mapping a to b simply just means that sigma of alpha is equal to beta. So let's write that out. So by the hints, there exists, I'm just going to call it phi or phi, might find it easier to write. So there exists phi from f adjoint alpha to f adjoint beta. Beta, and again it fixes f, so fixing f and mapping alpha to beta. Again, that just means that phi or phi of alpha is equal to beta. And from here we can then manipulate a little bit, right? So have then, and we'll start with this right over here. It's going to be useful because we can take phi or phi of both sides and make use of some of the properties that we have about phi. Again, it's an isomorphism, it maps alpha to beta, and it also fixes f pointwise. So we'll definitely make use of all of that. So here we have f to the m alpha minus 1th derivative of alpha. We know this is equal to 0. And then from here we can draw some implications. So we can apply phi or phi to both sides. So phi or phi of this right over here. And this is equal to phi or phi of 0. And here I'm going to make use of a property of the isomorphism we have over here. Again, remember that isomorphisms, they respect addition and multiplication. So here effectively we can move or apply phi directly to alpha, and I'll write a bit of a note at the end of this question as to why. But for now, so we have f, this derivative of phi of alpha is equal to, and again, 0 is just a 0 element of this field, I believe we just called it f, yeah, f that we're working in. And because phi or phi, it's an isomorphism that fixes f pointwise, fixes f pointwise, we know that it must send 0 to 0. So this is just equal to 0. But again, very important that we're making use of this hint. Phi of alpha, or phi, it maps alpha to beta, right? So we know that this then becomes, m alpha minus 1 of just beta is equal to 0. But this contradicts exactly what we had right over here, right? We were, like, based on our assumption over here, we were able to deduce that this function evaluated at beta was not equal to 0, but this clearly shows that it is actually equal to 0, which is a contradiction. And so this over here contradicts m alpha minus 1 of beta not equal to 0, right? So it contradicts this, and so just by proof by contradiction, we know that our assumption here must have been false, and we're allowed to conclude that this right here, so that all zeros have the same multiplicity, is indeed true. So let's quickly write that out here. So therefore, all the zeros of f of x, I guess in E, have the same multiplicity. So that's question 5, and I'll quickly go over a note down over here as to why we're actually able to make use of this right over here. So let's just say we have some generic polynomial, it's f of x, let's say it's of the form, let's say 0 plus a1x, all the way up to an x to the n. And here we're going to assume that phi or phi, it's an isomorphism, so, and it also fixes the elements in the field pointwise. So again, it respects addition and multiplication, and that's going to be really useful here in that sense. So here, we're going to apply phi or phi to both sides, so phi of f of x. Again, this is the same as just applying phi to this entire side, but because it respects addition and multiplication, first we're going to use the fact that it respects addition, so we can effectively apply phi to each of these kind of terms. So you have phi of a0, phi of a1x, all the way up to phi of an x to the n. So that's again using the fact that it respects addition. And now we're going to use the fact that it respects multiplication as well, and then we'll use the fact that it fixes the field pointwise. So plus phi of a1, phi of x, all the way up to phi of an, phi of x to the n. And now because it fixes the field pointwise, which is where all these coefficients are coming from, we know that phi of a0 and all these ai's are just going to be themselves. So a0 plus a1 phi of x, all the way up to an phi of x to the n. But notice that this is precisely the same as moving this phi inside of here effectively. So this is the same thing as f evaluated at whatever phi of x is, right? We've effectively just replaced all of the x's with phi or phi, and that's exactly what we used in this step over here to kind of bring the phi or phi into what we were evaluating at, which then allowed us to make use of the fact that, phi maps alpha to beta as well. So that's question 5. Question 6, so we're letting f be the Galois field of 2 elements, and E be the Galois field of 2 to the 2 elements. And again, we're reminded that E over here, it can be expressed as precisely this, just Z2 adjoined alpha, right? So we have 0, 1, alpha, and 1 plus alpha. So let's take a look at part A. So in part A, we want to show that the degree of the field extension is equal to the size of the Galois group of E over F, or just Galois of E over F. So first, we'll note that, and we're kind of making use of what we saw previously, that E over here, which is the Galois field of 2 to the 2, or just 4 elements, it's actually the splitting field. So splitting field of x to the 2 to the 2, such as x to the 4, minus x. And of course, we can further factor this. So we can factor this, factor out x, so we get x cubed minus 1. And then we can further factor this into x minus 1 times x squared plus x plus 1. And now we note that x and this x minus 1 term don't cause us any problems. All of their roots are indeed in z2, right? Just 0 and 1. But this term right over here does cause us some problems. So we want to show that it's irreducible, so we can eventually adjoin a root to z2 so that it does eventually split. So we can eventually also find its splitting field as well. So as before, so I'll quickly write this here. So since x squared plus x plus 1, it's a degree 2 polynomial, we can show that, or it's enough to conclude that, so it is irreducible, in this case over z2, if and only if it has no roots. So it has no roots in z2. And of course, this is much easier to check than z5, even though z5 wasn't that bad. we simply just have to evaluate this polynomial at 0 and 1, which are the only elements of z2. So let's just say, we'll just set this equal to f of x, so let f of x be that polynomial, so x squared plus x plus 1. And now we can just evaluate f at 0 and 1. So we see f of 0 is just equal to 0 plus 0 plus 1. It's obviously not 0. And then we have f of 1, which is 1 plus 1 plus 1, which is 3, which in mod 2, or z mod 2, it's just 1, which again is not 0. So this is enough to conclude that f of x is, I'm going to shorthand it here, irreducible over z2. Then we can make use of this notion of separability, which effectively just tells you that if you were to factor a polynomial or rewrite it in terms of irreducible factors, none of those factors have repeated roots. And in our case, we just again showed that this right over here is irreducible, and obviously linear terms are always irreducible, just by the definition of irreducibility. So because we showed that this right over here is indeed irreducible and it clearly has no repeated roots, we can claim that this polynomial is actually separable. All right, so let me quickly write that out. So clearly, none of the irreducible factors have repeated roots. And from this, again, as I mentioned, so x to the 4 minus x is separable. So similar to what we saw before, we can just join some root alpha. So just say let alpha be a root of f of x. Then we know that the Galois fields 2 to the 2 elements. This is just simply z2 joined alpha, which again, which is the splitting field of x squared plus x plus 1 as well. And so from this, we can conclude that, so thus, the degree of this field extension here, E over F, which again, we can just replace with, I guess, what they actually are. So in this case, GF2, so Galois field of 2 to the 2 over Z mod 2, which again is obviously just equivalent to Z2 joined alpha over Z2, which of course is just a degree 2 extension because alpha here is kind of a degree 2 element in some sense. And from here, we can finally just invoke theorem 56, which just requires that the polynomial we're dealing with is separable, and that the extension here is actually the splitting field, which is exactly what we have in our case. And theorem 56 allows us to conclude exactly what we want over here, and that the degree of the field extension is just equal to the size of the Galois group. So by theorem 56, the order of the Galois group of E over F is just equal to the degree of E over F, which in this case, again, we saw it was just equal to 2. That's all we need for part A. So let's take a look at part B. Right, so part B, we're just looking for the Galois group itself, so Galois of E over F. Right, so from part A, we have that the size of the Galois group, E over F, is just equal to 2. And since Z2 only has 2 elements, and just from group theory, we know that's the only group with 2 elements, we can just directly conclude that the Galois group of E over F is simply just isomorphic to Z2. Right, so since Z2 is the only group of order 2, and again, this is up to isomorphism, of course, we have that the Galois of E over F is isomorphic to Z2. And if you want to be more explicit with it, we can just say that, so yeah, more explicitly. The Galois group of E over F. Again, remember this is just a group of permutations or just automorphisms. This is the set. So we have the identity, and then we just have one permutation over here, sigma. And then, yeah, so we're sigma here just maps alpha to alpha plus 1, I believe. And that's question 6. Question 7. So let E be the splitting field of a cubic polynomial f of x in the ring of polynomials with coefficients in Q, so rational coefficients. And we're supposing that the Galois group of E over Q is a cyclic group of order 3. So let's take a look at part A. We want to show that the degree of the extension E over Q is 3. So let's write that out. So first, we note that since Q here is a field with characteristic 0, characteristic 0, and again you can get into the definition, but it basically just means that once you keep adding an element, you're never going to get to 0. It's unlike Z mod P, where if you add a number P times, you'll eventually get to 0. But a property of fields with characteristic 0 is that every non-constant polynomial is actually separable. Right? So because we have this, every non-constant polynomial is separable. And again, we've been over this previously, but this simply just means that once you rewrite your polynomial into irreducible factors, all of those individual irreducible factors have no repeated roots. So here again, we're going to invoke theorem 56. So again, by theorem 56, we have that the order of the Galois group, so Galois of E over F, is equal to the degree of the field extension. And so this is going to be very helpful here, of course. So clearly in the question, we're given that the Galois of E over Q is the cyclic group of order 3. So of course, the order of Galois of E over Q, it's equal to 3, which is also going to equal to the degree of this extension E over Q. And that's all we need for part A. So now let's take a look at part B. We want to show that all the roots of f of x must be real. Of course, similar to the previous question about multiplicity, it's easier to show this by contradiction. So let's do that. So B, so suppose for contradiction that f of x has a complex root. And let's just call it beta. So complex root beta. So because complex roots come in conjugate pairs, we know that we also have another root. Let's just call it beta bar. So again, since complex roots, and they come in conjugate pairs, so come in conjugate pairs, we know that beta bar is also a root. Root of f of x. Together though, because we do have complex number and again the complex conjugate, it means that complex conjugation must be an element of some subgroup of the Galois group or even the Galois group itself, right? We just know that complex conjugation definitely has to be in there somewhere. So let's write that out. So this means that there must be a subgroup of our Galois group of Galois of E over Q. Oops, E over Q generated by complex conjugation. Right, and again, the kind of diagram you can envision is we have E over here, and then we have Q adjoin beta, and then Q itself, right? So we're looking at the entire Galois group, but of course there's going to be a subgroup somewhere in here that must also just contain complex conjugation. So let's just say sigma here. So let sigma be complex conjugation. And so now we can look at the cyclic subgroup generated by it. So sigma here, we just have the identity, of course, and then sigma itself. And this is all we have because if you conjugate twice, you just get back to the identity. So we have a subgroup here of order 2, and we'll see in a second that this is indeed problematic. So, however, this right here, so this is a subgroup of order 2 of that Galois group, so of Galois of E over Q. And of course, as we've seen previously, which it has order 3. And of course, this is a problem by Lagrange's theorem. We know that the order of the subgroup must divide the order of the group itself, but of course 2 doesn't divide 3, right? So we know that Galois of E over Q cannot have an order 2 subgroup. Again, by Lagrange's theorem. And so all roots of f of x must indeed be real. So must be real. Question 8. So let R be the set over here. It's the ring of all continuous functions from this interval 0 to 1 to the real numbers. Let's take a look at part A. So for any element C in this interval over here, we want to prove that this set here, M sub C, defined as the set of functions in our set R such that f of C is equal to 0. And we want to show that it's a maximal ideal of R. And then the hint is to consider the evaluation map at E, which is going to be a very helpful hint, in fact. So let's begin. So in part A here, I'm going to let E sub C here, and it's again going from R here to the real numbers. Again, this is not to be confused with the real numbers. This is the set we have over here. And the function or the mapping here, it's given by, it's going to map elements from here, which are functions in F. And they're going to be mapped to just F of C, which is of course going to be a real number. So EC here is, or again, the evaluation map at C is indeed a ring homomorphism. In fact, it's also surjective, but these are all things that you can definitely try out as an exercise. It's not too difficult. You just have to show that it preserves addition, multiplication, and it maps 1 to 1. And then for surjectivity, we'll see in a second as well, but the overall idea with surjectivity is that if you take any function here, so again, just by definition, with surjectivity, if we look at this map over here, for any elements, let's just call it B in the real numbers, we want to say that there exists some element in R, so F in R, such that the evaluation map, so EC of F, is equal to, I guess, B in this case. Maybe we should call this C. It's equal to C. And of course, what this then means is that f of c must equal to c. But of course, we can just take the constant function, or the constant polynomial, and of course, we can always find that it's always defined, especially on this interval 0 to 1. So that shows that it's also surjective. But those, again, are just quick notes on surjectivity and showing that it's a ring homomorphism. Definitely not too difficult to show. On an exam, it's safest to show it, but for our purposes here, we'll just omit that for now. So next, we'll make a quick note. So we can note that MC over here, so M sub C here is precisely, so it's precisely the kernel, actually, so kernel of our evaluation map here, right? So our evaluation map is again given by this, and the kernel of the evaluation map is simply just the set of elements that get mapped to 0. And this is actually just precisely that, which is really helpful, right? Because so this means that MC here is an ideal. Right, so that's already helpful. Right? We want to show that it's a maximal ideal of R. We've already showed that it's an ideal at least now, so this is good. What we're going to do next is we're going to consider the quotient ring now. So next, we can consider this quotient ring here of R mod M sub C. So the result we're going to eventually use here, we're going to use a combination of the first isomorphism theorem as well as a result about quotient rings, which are definitely in the textbook, widely used throughout, so definitely be familiar with them. But the overall idea is that R mod MC, in this case we'll use R and I just to be more general. So R mod I here, this is a field if and only if I here is maximal. So through first isomorphism theorem, we'll eventually show that this is actually indeed isomorphic to the real numbers, which is of course a field. And then from that we can use that to conclude that M sub C is indeed maximal as well. So let's do that. So the first isomorphism theorem, this gives us that. So it gives us that there is an isomorphism. So there is an isomorphism so it's from this quotient ring here, so R mod MC to the image of the evaluation map here, which of course we, by the surjectivity claim that we made, this is just isomorphic to all of R, right? So normally with first isomorphism, we're looking at R mod the kernel of the map that we're looking for, but of course we already just claimed and showed that M sub C is just the kernel of the evaluation map. And so with this, we have that R mod I, or M sub C, is actually just isomorphic to R, which is a field. And then again, as I mentioned earlier, so since an ideal is maximal, again, meaning it has no intermediate ideals between the ring itself and the ideal. So it's maximal if and only if the quotient ring is indeed a field, which we just showed it is. Fields. We can then conclude MC is a maximal ideal. As needed. That's it for part A. And so for part B, I'm actually going to omit part B simply because the solution that was given in class or through the review session, somehow he made use of topology, which I have no experience or knowledge in. So if you want to give part B a try without it, somehow, some way, feel free to go ahead, but for our purposes, we will definitely end here. So thank you for watching up to this point. I probably should have mentioned this at the beginning of the video, but of course, I'm going to be posting all of the resources that I've gone through in this video, more so the blank copy as well as my own written solutions in the comments as well, and I'll also link the videos to my resource guides as well as anything else I might find helpful that you also might find helpful in your studies. So again, thank you for watching, and as always, feel free to reach out if you have any questions, concerns about the material, or anything else.